Hi all, first of all, thank you for making it. And I'm here today to talk to you about developing a safety test framework in U-Boot for automotive applications. So a little bit about TI again. We heavily prioritize an upstream first mentality where we try to get all the code into the mainline before we pull it into our SDKs. And we've had years of collaborative efforts, as you can see with the many projects on the screen. Short intro about me. My name is Neha Malcolm Francis. I am a software engineer at Texas Instruments, and I work from Bangalore, India. I primarily work on U-Boot, along with a few other IPs like UFS and DDR. And I focus on boot for our automotive line of SoCs called Jacinto. And when you don't find me working on U-Boot, I'll most probably doing one of the many hobbies I have. So. Quick disclaimer, this is a tech-related presentation. It's not a product readiness or any kind of fulfillment or roadmap. And the opinions here are of my own and may or may not be that of Texas Instruments. OK, let's start with an overview. Before that, I just want to give you a brief mental picture of why I started with this topic in the first place. So a few months back, we had a customer that came up to us and wanted to implement a safety feature that they were trying to put in on a mixed criticality system. And if you don't know about mixed criticality systems, I'll quickly cover that as well later. But this was their proposition. And they wanted to implement this in U-Boot. So that's when I got into what U-Boot has to offer. And turns out there's a lot more that we'll have to deep dive into during this presentation. So we were able to get the driver upstreamed, but yeah, let's move ahead with the talk. So I'll start with Linux, using Linux in safety critical systems, and move over to how it's used in open source bootloaders and where are we with safety certifying them. I'll talk a little bit about mixed criticality systems and using U-Boot in such use cases. And then finally, converging on why we need to have a safety test framework in U-Boot. So another small presentation-related disclaimer. The title might be a little misleading, but I'm not here to explain about the implementation level details, which might be trivial, just creating a new subsystem. But the focus is on why and how we need it right now, especially since it's not there. So let's talk about Linux in the automotive systems, which are safety critical. There's a lot of advantages that make adopting Linux very tempting, right? For example, you have heterogeneous compute support. There's a rich hardware platform support. And due to the rich hardware platform support, it's easy to port from one platform to the other if you're an SoC vendor, compared to really putting in the work for porting an RTOS. And there is the cheap development cost that comes with having multiple developers all over the world, and you are working on common code. Security capabilities, far advanced in Linux than you see anywhere else. When you think of features, you think of SE Linux, but you also have the advantage of so many people looking at your code and ensuring that there's no gaps anywhere. So that is an edge that Linux provides. And of course, everything else that comes with it being open source. The transparent code quality that we have, and it is a meritocratic development. So you ensure that simple, robust code gets in. So it makes sense why big guys like Tesla have had Linux in their operating systems. And yeah, so they do make use of the ecosystem. So there are a few cons. I would rather call them excuses than cons for not picking up Linux. One is RT, but hey, last year we've solved that issue. So the community pushed, and now it's not so much an excuse. Next is it's a monolithic kernel. That's also another common problem that people face when they say, hey, I'm trying to adopt Linux compared to something else. Yeah, it's not something that's solved, but it's not something that you can't get your way over, right? So Linux is Zen enabled, so you can use a hypervisor designed system and kind of move around. It's still monolithic, but you have ways around it, right? So next is insufficient testing, but we know that, I think there was a talk yesterday as well about the huge number of static analysis, dynamic analysis. We have code coverage tools. And on top of that, we have kernel CI. So testing is also not really a big problem. Then we come to safety compliance. Again, I'm still talking about Linux, so we'll get into safety compliance in Linux. So there have been huge, tremendous, very important strides towards moving to safety compliance in Linux. Since this is not the Safety Critical Summit, I assume some of y'all might not know about this different projects that are already existing today, so I'll also quickly list them out. You have the OSADL SIL2 Linux MP project. They're working on defining methodologies to qualify Linux, and they focus on multi-core embedded platforms, and they aim for a SIL2 level, and it's open. You have ELISA, everyone knows ELISA. They're also defining and maintaining processes that can safety certify Linux. It's also open. You have AGL. AGL is also actively developing a platform for automotive applications. And thanks to AGL, you have other projects that have sort of stemmed out from it, like RHIVOS, which is the Red Hat in-vehicle operating system. They also target functional safety certification in Linux. And it's not completely open, but you can base your code on AGLs and somehow understand what they're trying to do. So it's still there. Now, OpenAMP, I've put it here. It's not that it's related to safety. However, I want to showcase how there are so many standardizations that are happening in Linux right now that really accelerate safety certification. Heterogeneous communication is something that in any complex system you need to have, and automotive systems they're not any different. So OpenAMP really makes a good progress over there. So it's not safety specific, but it helps. So now the important question is, where are we with bootloaders? Certification typically involves you certify all your components. So you start with bootloader, then you also certify your kernel, you certify your root file system. And the bootloader is very crucial, and it will definitely be certified. But in this talk here today, I really want to focus on open source bootloaders. And what are we doing with open source bootloaders? Is there any progress towards certifying it or not? So short answer, not really. And this makes sense because the burden of safety certifying your bootloader is usually on the SoC vendor. They're closer to the hardware. They know exactly how to safety certify their bootloaders, and they create their own proprietary bootloaders. And typically the trend is they start writing these RTOS bootloaders keeping safety in mind, whereas with open source bootloaders, we didn't start writing it with that in mind. So it's understandable how the final boot flow typically looks like. Your proprietary bootloader comes up first, which boots up Linux. Now there's advantages and disadvantages to this. The advantage is what I mentioned now. It is safety conscious. They've written it with safety in mind. However, it comes with a high development cost. In the sense you need to have both effort and time to get to the latest and greatest technology when it comes to any proprietary bootloader. So, But in comparison, you have an open source bootloader, which is the exact opposite. You're at the bleeding edge of technology, but not really safety conscious. So with that, let's talk about U-boot specifically. Now, U-boot is quite rich. It has a lot of the typical ammunition that it carries. Like, it has so much peripheral drivers. It has a lot of stacks. It supports multiple architectures like ARM, x86, RISC-V. And a very important part, since we're talking about the Linux ecosystem, U-boot is tightly coupled with the Linux kernel. And this is a huge advantage when you compare it with developing anything else. And specific to automotive, There are a lot of advantages. For example, it has OTA update support, it supports secure boot or verified boot, and it also supports device tree support. Now, device tree, even in kernel, you know the advantages, but even in bootloaders, it has tremendous values because you are working with multiple ECUs and you need to have a single bootloader image that can have different device tree configurations, which U-boot supports. And that is an advantage for using it within Automotive. So now that I've talked about all the pros of U-boot, it's not like U-boot isn't used anywhere. In fact, it's used more than we think. So I've listed down a few of the projects. They're both automotive and space. EB Corbus is a ECU software solution by Electrobit. You have RHIVOS and AGL, which I mentioned before. They use U-boot. And SpaceX Falcon 9, which is a commercial rocket with humans, they also use U-boot. So all of them use U-boot. They probably internally had some kind of certification done or some kind of analysis done on U-boot. And most likely, they were either modified to support or to adhere to certain safety standards, or the more probable reason is they've used some kind of mixed criticality system, which we'll again talk about later. And while I was looking through all of these projects, there's this quote that I came across from some article or blog, which is, we try to keep our program simple, slim, and based on code we understand throughout. And this really makes sense because, this is a slight interjection here, this quote. And they're not really talking about open source software in specific. They're talking about their development and design methodology. But it does make sense for why they chose to use open source software. Because writing simple, robust code is at the core of open source software right now. So it's not that you're ensuring that there's no safety risk, but it does ease it to some extent because you see your code and you know exactly what you're doing. But all in all, proprietary bootloaders are they do pretty well. And you can see a lot of these embedded, a lot of these automotive vendors are all using their own proprietary bootloaders, including Texas Instruments. Our automotive chips also come with a proprietary secondary bootloader, which is most commonly used. And yeah, you can see Vector, Electrobit again, they also have an ACO bootloader. So they're doing pretty well. So now we come back to U-boot, and is it possible to safety certify U-boot? Now, I'm not a safety expert, but the discussion has to happen somewhere. So is it even possible? It's a reach, but it's not impossible. So what are some of the ways we can maybe start this discussion? We could probably start with a FMEA, FTA analysis and figure out what are the gaps. The next thing is testing. Testing is already quite solid in U-boot. There are a few gaps, but it's quite broad. And U-boot is also in Coverity. So you have static analysis. And we support sandbox testing. So without the hardware, without access to hardware, you can still make sure you have coverage. And the issue with a project like U-boot, which is so large, is the fact that it supports so many hardware configurations. So unlike the kernel, which also supports so many configurations, but you kind of have a generic kernel image for an architecture and you can test on it. But for bootloaders, it's not the case. You're either you're specific to a hardware configuration as well as a boot flow configuration. So it's like a sub configuration, and you have all these probably tens to thousands of boot flows that you'll have to verify. So is it possible to maybe define a minimal and well-bounded configuration? That's also something that you can look at. And the last is, can we rewrite some of the critical code in Rust? Does it even make sense? So all of these are topics that I think individually need a lot of discussion on, and we'll have to figure things out. So there is clearly a long way to go. So can we, but what can we aim at right now? What do we have right now? What can we make better right now? So now coming to mixed criticality systems, What is a MCS? So an MCS allows varying levels of safety requirements to coexist on the same hardware platform. So most of the time, if you've worked with hypervisors, it's achieved using hypervisor support with partitioning. But the end goal is your fault is contained within your non-critical system. So it's important to analyze any kind of communication between either your partitions or your cores need to be fault isolated. So an example use case within the automotive domain would be IVI systems that require some kind of VertIO or PV devices which need higher complexity, but they're okay with being relaxed on lower safety levels. At the same time, you can have them on automotive systems with safety channels at the side. So, yeah. So such systems, they ensure fault isolation, as mentioned. And it's not just fault isolation, but there's another advantage with this fault isolation, which is selectively recovering your system. So the advantage is if your whole system burns down to the ground, your whole system doesn't burn down to the ground, at least the ones that did, you can recover and ensure that there's no risk of injury or damage. And as you can see, the automotive space is using MCS most of the time. And it's pretty reasonable why they do it, right? So one is reducing certification work. It's quite obvious that it's a lot of development time and cost time that you save on. The next is ECU consolidation. So the end goal right now is to decrease the number of ECUs you have on your vehicle by grouping some of them, maybe under you call it a domain controller or a centralized unit, but you reduce the wiring and the weight of your vehicle. So this is up and coming right now in most of your SDVs. And thanks to the first 2 points, you have a reduced development cost and a faster time to market. So it's a no-brainer that SDVs are using this right now. And when it comes to Linux, it's obvious. It's a very clear choice or a clear competitor, at least, for enabling the whole system or at least a part of the system. But why should U-boot be the choice of bootloader in that case? So now we'll talk about how can we prep a bootloader to work in such systems. Now, besides the obvious, which is initializing hardware and doing everything that you need to get your kernel up to boot, in an automotive system, the bootloader also needs to, one, support OTA updates, support secure boot, and support diagnostic testing. Now, what we covered earlier, we know that U-boot supports OTA updates and secure boot. But is it supporting diagnostic testing? This is the question. So we can increase the safety chapter of U-boot by supporting diagnostic testing, which is a gap here today. So whatever advantages I told back then about U-boot and why we need to start using open source bootloaders here, you pair that with the advantages of making it a little bit more relevant in a safety context, you're really hitting and getting a double-edged sword. So in MCS, one of the ways to do this is the bootloader can execute a fault diagnostic test prior to running some kind of safety application. So an example, a very common example, is enabling ECC on memory, if there's any. There was a patch series that went in, I think, last week, where they enabled ECC on L1, L2 cache of A72, but this was in the Linux kernel. But I haven't gone into the details of that patch, but it's something that U-boot could have done earlier, and then you move to the kernel instead of the kernel doing it. So that enabling ECC on memory is something. ECC on RAM is also something that U-boot already supports, at least for the K3, TI K3 architecture of devices, and I'm sure a lot more. But there's still scope for more. And the next thing that you can do is check for any CPU faults. And this brings us to the hardware IP called the BIST, or the built-in self-test, which does exactly this. So let's just talk a little bit about this IP, which is a hardware block. It is a diagnostic block that tests both your memory areas and the logic circuitry of your IC at boot time. So this is a fancy diagram that just basically says you have a test controller, you prep up your circuit, which is under test, and ensure that it's ready to undergo your fault diagnostic test. You apply some stimulus that starts this test, and then you just analyze your output and see whether your logic circuitry and your memory is good to go. So this enhances system reliability greatly. And it's also expected to be run only once at boot time. This might be a hardware implementation. It could differ. Maybe there are implementations where you can run it more than once, probably as a periodic check. But the one that was implemented in the chip that I worked with expected it to be run only once. It's destructive in nature, typically, and it cannot be performed by applications at runtime without saving or restoring context. Again, this is assuming that you can do it more than once. So the customer request, back to the initial statement that I was talking about, they wanted to trigger BIST from a non-safe U-boot on 2 cores that were on their own safety channels running their safety certified firmware. So this was the proposition that they brought. And the BIST driver, we got it upstreamed with some back and forth. And it was when I submitted this talk, it wasn't upstreamed, but now it is. So you can have a look at it if you get the time. But let's talk about what is the flow that they went with. So if you look at the diagram, you have 3 columns. The leftmost is your non-safe, your A72 running your non-safe U-boot. And the other 2 are your R5 cores. You don't have to look at the prefix or postfix. That's just nomenclature within TI. So, but essentially they're 2 R5 cores, which were there the customer's safety channels. So I've cropped out a bunch of the extra additional boot flow, which isn't relevant right now. But you can see at reset, you start your ATF and Opti, and then your A72 SPL U-boot starts running, which triggers the BIST using the BIST driver on these 2 other cores. And post that, it starts running the U-boot proper, which at least in the development stages was responsible for loading and starting the safe cores. And you can see once the firmware started running, the first thing that it did was read its own BIST result. So we kept the BIST result on some non-volatile memory that was shared, and the MCU code just read it and figured out that, okay, its hardware is good enough to go, and we can just proceed. So they were able to, at least they're achieving a system level Cat3 certification using this flow. And you can just see the BIST device tree node that was used for this. Now, talking about safety IPs in U-boot, is the miscellaneous directory good enough to house the BIST driver? It's good enough, but it's good enough seeing that there's only one of its kind right now. But there are many possibilities of other safety IPs getting into U-boot, and it's becoming more relevant. So JTAG, as we all know and love, is not just for debugging or programmability. You can run boundary scan tests on it or trigger it at boot time. So there's scope for that. You have SDL and STL ARM libraries that they ship out right now, which have both runtime and boot time tests. So we could make use of that. And eventually, we could move from using the miscellaneous directory to these safety directories. So to conclude, there's a large scope for introducing these IPs within U-boot and starting up a safety test framework. So the BIST driver is hopefully one of the first of many more drivers that can go in. And eventually, we'll be able to fill in those gaps, at least for the mixed criticality systems, and then work our ways towards having a safety certified open source bootloader. So yeah, this is all part of that effort to make sure U-boot is relevant. And some of the references that I've used are also put up here. I'd also like to thank Texas Instruments, the Linux Foundation, and some of my colleagues, Kevin and Bileshwar, as well as the SDL team back in Bangalore and the U-Boot community. So yeah, that's it. And if there are any questions. No questions?
I have one.
Okay.
Maybe do you use the whole U-Boot for this whole thing, or do you use only the STL and then you boot Linux from there?
Yeah. So this was one of the challenges that came up that was specific to the TI architecture. We use SPL and then we come up to U-Boot and then go ahead with it. But this is for development. So I assume the customer at some point removed the U-Boot proper and just probably went just with the SPL triggering BIST and then moved forward. Yeah. Yeah.
I have a problem with this BIST type. When you have a processor that checks the processor, then you have a catch-22, because you have to make sure that the processor that tests is okay. How do you think that can be solved?
Yeah, that's a good question. So in their specific boot flow, one thing that they did is the safe core is reading its own result. That's one. But again, your question is still valid even if it's reading its own result. But from my limited understanding, what I know is false positives are the notorious things you don't want. A false negative would still be okay because you'll still know that there's something wrong, even if it wasn't, and you can do some kind of error handling. But false positives are where we need to catch it, and that's more rare. So again, the concept of a mixed criticality system comes into play, where these are not as critical as the other partitions or cores that are running something else. So yeah, it's a give and take. So the idea is it's not about safety certifying the whole U-Boot, which would be the best way to go, but I still want to make it relevant in such cases and just give it a little bit more ammunition than it has today. Yeah.
Testing is very tricky.
Yeah. Yeah.
Another one. Do you think about a standard way to report errors? Because I expect it works.
Yeah.
But I would like to have a standard way to tell me it does not work.
Standard way specific to the U-Boot community or? Okay.
You don't have anything.
Right. I don't think there's anything right now, but I'll take that into account. At least we have to start the discussion somewhere. So yeah. Yeah. Did you?
Actually, there is a kind of a different question.
Okay.
The BIST is a one-time operation. Is that correct? So
Yeah.
you reach some point in the flow, and then you ask the BIST IP, is everything okay?
So the BIST IP is just trying to run a few tests. It has a sequence that it imposes on the circuitry, and then it expects another sequence to follow up at the end. So it has, I think, multiple such sequences, and it keeps going on, tries to see if the end output is the same as what it expects. So it's separate from the IP that is triggering it. It's just going to be on the IP under test, if that makes sense. Yeah.
You could do test hardware unit testing,
Yeah, I didn't repeat the questions, but I hope it's understood.
Then hardware error detection, right?
I think so.
You can have some sort of an error detection, which probably is
Yeah.
asking about.
Yeah, this is not error detection, no. Yeah. But yeah, that's also something, there are so many error detections right now. ECC in RAM is the most common one that you can see on U-Boot. Nothing more than that, but I'm sure every SoC vendor has some something that they've done in their RTOS bootloader that's not currently there in their open source bootloader. So there's a lot of these popcorn IPs that haven't been taken care of that we can really push towards this framework eventually. Yeah.
Why do we need to run BIST? Because BIST is run anyway out of production normally to see whether the silicon is good or bad, right?
Yeah. So there's different kinds of BIST also. So they typically, I think for, again, this is what I understand, it's for boot time optimization. Usually ROM comes up and runs BIST on certain IPs that it thinks are very fundamental. In our case, we have a safety island, an MCU island that sits and you do BIST on it. So it's already safe and we know it's safe. But the A cores that's running Linux, the cores that I brought up that I was running BIST on, those don't have BIST because it still takes some amount of time. So you can run, there's two kinds of BIST. You have the logic BIST, which is the logic circuitry BIST, and the memory BIST. So typically what they do is they trigger one and let it continue, and then they trigger the other one. But they have to wait for it to finish before proceeding with the boot flow. So in that case, I'm guessing maybe because of boot time, they don't check the whole system. So this exists today. Yeah. Yeah. Any other questions?
Well, I may have one.
Yeah.
You used to have post functionality.
Okay.
Have you run across that? But this is something which
Okay.
is there since the beginning of times, and it could be maybe inflexible for different implementation.
Okay.
Have you seen that?
I've seen post, but isn't it power on self-test? So at power on.
The question is whether you could wire the BIST into it.
Yeah. So
When the post happens, trigger also the BIST.
correct. So that's what I was telling him as well. So there is, that functionality is in place, but due to the time, you only limit it to the area that is very crucial. Most likely the safety island that you have. And then you just run BIST on those cores. But the other cores that are implementing a lot of your automotive, like the C7X, your other A cores for higher performance, whatever compute clusters you have, those probably did not have BIST run. They're not as important. They are important, but